Honors Chemistry. This is the pretest review. This is to prepare you for the district final, which will be on June 8th and 9th, depending on which period you're in. This is going to also count as your midterm, so it's 10% of your total grade to do this. I'm going to do every problem. You just need to go ahead and do them. This is due on June the 14th, which is a Monday. However, you should have it done before you take the test on either June the 8th or June the 9th. Okay, this will lead you through a lot of the questions. All right, so let's go ahead and get started on this. So what two things did Rutherford's gold foil experiment discover about the atom? And those two things are: one, it has a solid nucleus. So one, it has a solid nucleus, a small condensed solid positively charged nucleus. It's protons. And two, it's made up mostly of empty space. Okay, the next one is going to be for questions 2 and 3. So here we have a chemical reaction. It's an endothermic reaction because heat goes in on the reactant side. You treat heat like a reactant, so it goes into the reaction to make it move from left to right. Okay, so which way does the reaction move, left or right, to this reaction when the increase in Cl2 molecules is increased, which should be when the concentration of Cl2 molecules is increased. So I'll change that. And you just think of the concept of a crowded room. If you assume this reaction is in equilibrium and you increase this goes up, the concentration, the reaction is going to want to flow back. It has more Cl2 than it would like to have at equilibrium if you increase that concentration, so it wants to flow backwards. It wants to take the products and turn them back into reactants. So that's going to be to the left. And I'm going to tell you, on these answers, you don't have to give me complete sentences. Just get down the answer, okay? That's good enough for that one, all right? Okay, which way does the reaction move if it were cooled? And again, you have to put heat in to get the reaction to move from left to right. So if you cool it, you're not putting the heat in. So that means the reaction is not going to move to the right. It's going to also move to the left. So we're going to go ahead and put that one in right there. Okay, it's going to move to the left if you cool the reaction. Okay, name two elements that form a 2+ charge. So for this test, you really just need a periodic table, but you're allowed to use any of your notes, and some of the other tables, some of the other reference sheets that you have might be helpful. So 2+ charge. Well, let's assume you don't. There's some of the transition metals that have 2+ charges, but you know that everything in the second column has a 2+ charge because it wants to lose 2 electrons to be like the nearest noble gas. So beryllium will lose 2 electrons to be like helium. Magnesium will lose 2 electrons to be like neon. Calcium will lose 2 electrons to be like argon, and so on and so forth. So you can really pick any of the elements here. Those are 2+ charges. If you have the periodic table that shows all the charge numbers, you can go ahead and use that. Okay, so we're gonna say Mg and Ca. All right, number 5. A solution has a hydronium ion concentration, remember that's the shorthand version, can also be written H3O+, of 1.0 times 10 to the -6 concentration. If water is added to dilute the solution, which way will the pH move, up or down? Okay, so you have an acidic solution. You add water, you're making it less acidic, you're diluting it. Again, think of the lemonade. You have lemonade, it has a certain strength to it. If you start pouring water into it, then the lemonade is going to become weaker and weaker. It's not going to be as sweet, it's not going to be as thick. Same with the acid. The acid is going to become less acidic. So remember, pH of 0 is most acidic, and pH of 14 is least acidic. So this acid in this example is going to become less acidic. That means for this one, the pH will go up. Goes up means a weaker acid. Okay, so there's the answer to the question there. Okay? All right. Name 3 acids that fully dissociate. So those would be the strong acids. There's 7 of them. I'm just asking you to name 3. So fully dissociate means that they're strong acids. Okay? So you have nitric acid would be one. You can have sulfuric acid. You can have hydrochloric acid. You can have perchloric acid. You can have chloric acid. You can have hydrobromic acid. I'll come over here. And you can have hydroiodic acid. Okay, 1, 2, 3, 4, 5, 6, 7. So those are the 7. You could pick any of those 3. All right, number 7. What is the density of a liquid that has a mass of 6.7 grams and occupies a space of 4.2 centimeters cubed? So this is the mass, this is the volume. Density equals mass over volume. It's how much mass you're crowding into a certain amount of space. Okay, that's the way to think of it. The more mass you crowd into a certain amount of space, the more dense it is. So this is simply going to be 6.7 grams divided by 4.2 centimeters cubed. Okay, and I'll let you do the math on that. Just 6.7 divided by 4.2, and the unit is grams per centimeter cubed. Okay, that's all there is for that one. Okay, give the number of neutrons, protons, electrons, and the mass number for the most common isotope of carbon. So if you come over here to the periodic table, there's carbon. It has 6 protons. That's the atomic number. It has an atomic mass of 12.01. Remember, that's the average mass of all of the different isotopes of carbon. Since that number is closest to 12, then that's the most common isotope of carbon, has a mass number of 12. There's a few that have a mass number of 13, even fewer have a mass number of 14, so you average all that out and you get a 12.01. But the most common isotope, well over 90% of carbons are 12, carbon 12. Okay, so it's asking you for protons, that's 6. Let's do mass number first. So the mass number we just said is 12. Okay, that's the total number of protons and neutrons. That means the number of neutrons, and I'll show you the calculation, is 12, that number minus the number of protons, and that's going to equal 6. Okay. And the number of electrons, assuming it's electrically neutral, is going to be the same as the number of protons. So it starts off electrically neutral, all atoms do. So it starts off with 6 electrons, okay? It didn't say it was ionized, an ion. If it was an ion, that would be a different number of electrons, okay? But it's not. It's just a regular atom. So those are the answers to that. Okay, so next one, isotope notation. Circle the pair of isotopes of the same element. Well, the top one is the mass number. It's total protons and neutrons. So I'm just using this as an example. That's number of protons plus number of neutrons. And the bottom one is the atomic number. And it's the number of protons. And it's the number of protons that defines an element. Okay? So an element can have different numbers of neutrons, different numbers of electrons, but whatever this element is, it's number 9. If we were saying that would have to be fluorine, because fluorine is number 9. So that defines the element. So the same element would be this one with 9 and this one with 9. This one has 10, so it would be a different element. Okay? So that's the answer for that. Okay, number 10. Calculate the molar mass of H2SO4. That would be sulfuric acid. So you just write H. You have 2 of those, and the atomic mass from the periodic table is 1.01 grams per mole. Since it's molar mass, we're dealing with grams and not atomic mass units. Next is S. You have one of those, and you come over here, and that's going to be 32.07. Finally, you have O. You have 4 of those, and those are exactly 16 from the periodic table. Okay, so we multiply that, we get 2.02. We multiply this, we get 32.07. And we multiply this, 4 times 16 is 64.00. And you add all these together, and you're going to get your mass. So I'm going to leave it for you to do that calculation. You just add 2.02 plus 32.07 plus 64. Okay, which radioactive particle is the least penetrative? And we talked about this. It's on the slides for nuclear chemistry. It's the alpha particle. It can be stopped by a piece of paper. Okay, so least penetrative means, and that's the words they use on the test, it means it cannot penetrate very far. So alpha is stopped by paper. The others, beta, gamma, X-ray can go through paper. They have more energy than alpha particles. Okay, there you go. All right. The half-life of a 20-gram sample is 12 hours. How much is left after 36 hours? Okay, so you can make a little table for this. So the first half-life is going to be 12 hours. You start with 20 grams, and half of that is gone after 12 hours. So then you end up with 12. The second half-life, you start with what you had at the end of the first half-life. Okay, and whoops, that's wrong. That's another 12 hours, okay? So it's 24 hours total, 12 plus 12. You started with 10 there, and you cut that in half, you get to 5. The third half-life, it's another 12 hours, so that brings you up to 36, and that's what the question is asking about. So you start with 5, you cut that in half, and you get 2.5. Okay, so that's the answer. 2.5 grams is left after 36 hours. Okay, that would be 3 half-lives. Okay, what would be the product of an alpha particle decay of U-235? So we said what an alpha particle was in nuclear chemistry. It's 2 protons plus 2 neutrons. And remember, that's the equivalent of a helium atom. Even though it doesn't come from a helium atom, it comes out of the nucleus of this uranium. It's the equivalent of a helium. I said a helium atom, I meant a helium nucleus. 2 protons, 2 neutrons is the equivalent of a helium nucleus. So the way you write this is U-235, so you have a U. 235 is the mass number. That's the total number of protons and neutrons. And then you have to come over to the periodic table and see that uranium is 92. That's how many protons. So we put that down here. Okay, so you're going to lose 2 protons. So that means whatever's over here is going to have 90 protons. So you have to go and see what element has 90 protons, because the protons define the element. Right there it's thorium. Okay, so that's TH. Now this is total number of protons and neutrons together, and it lost 2 protons and 2 neutrons. That's a total of 4. So this number is going to go down by 4, so that's going to be 231. Okay, and then what came out was the alpha particle, and we said that's the equivalent of a helium nucleus. So you write helium. It's 2 protons, and then 2 protons plus 2 neutrons, so that would be the mass number would be 4. Okay, and that's the answer. Now they're asking what would be the product. The product would simply be the thorium. Okay, I mean that's the entire reaction, but it's asking what's the product. Well, that is the product. It's everything. Okay. So anyway, that's it. Okay, draw a particulate diagram of the reaction. We talked about these, but I really didn't have you practice these. So just watch how you do it. It's not hard. So I'm going to draw a box. So this is reactants over here. And then they're going to lead to, over here on the right, to products. And it's just a picture of the chemical reaction. It's kind of what you did when you did the box method for balancing an equation. Okay, it kind of is like that. Okay, so you have 3A2. So I'm just going to go ahead and write that. And I'm going to write a little A inside of both of those. That's A2. It's basically like an H2, think of it, or an O2 or something. Okay, it doesn't matter where you draw these in the box. So we have 3 of those. Okay, then you have 2B. So you see B only has basically one atom to it. So we're just going to write that. That's B. And that's B. So those are the reactants. And over here, it's going to form 2 molecules that have 3 A atoms and 1 B atom. So you're going to have A. Let me draw the B here. B. A. A. Okay, so there's one A3B right there, and then we're going to draw a second one. Okay, and there it is. So those are 2 A3, 1, 2, 3, B. And you have 2 of them. Okay, and that's it. That's a particulate diagram. That's all you have to do for that. Okay, so it's not very hard. Okay, balance the equation. Now you get to balance an equation here. All right, so you can do it box method. You can do it the traditional method. So we will go ahead. I'm going to do it the more traditional method here. Boom. CHO. That's the only 3 elements. So count carbons on this side is 2. Carbons on this side is 1. Hydrogen on this side is 6. Hydrogens on this side is 2. Oxygens on this side is 2. And on this side it's 1 and 2 more. So 1, 2, 3. Okay, now this one's going to have a little trick to it, all right? Okay, so let's go ahead. Let's balance carbon first. So we're going to put a 2 here. Again, we write the coefficient up above because it may not be our final coefficient. So we have 2 carbons there, and that balances the 2 carbons there. So we change the carbon to a 2. But that 2 also changes it from 2 oxygen there to 4 oxygen. Now be careful. I gave you one here that has some tricks to it, so be sure you understand these. So you have 2 times 2 is 4, but you also still have that one. So that's 5. So in all, on this side, you have 5 oxygen. So be sure you understand that. So that's 5. Okay, hydrogen. You have 6 on this side. By the way, you want to save oxygen for the end. Why? Because it appears in more than one location on the right side, and it's by itself right here. If it's a lone element like that, you don't want to start with it. Okay, so hydrogen's going to be next. We have 2 on this side, and we have, we have 6 on this side and 2 on this side. So we're going to put a 3 there. So 3 times 2, we now have 6. Okay, but again, we changed the oxygen, so now we have 3. So now we have 3 oxygens there, 4 oxygens there. That's a total of 7. Okay, so we've got carbon and hydrogen in balance. Now we got to balance oxygen. We have 7 on this side, 2 on this side. So this is one where you have to do this fraction thing. So you've got 3 on this side plus 4 more. That's 7, so you need 7 on this side. What do you multiply 2 by to get 7? Well, you multiply it by 3.5. 2 times 3.5 is 7. Or the way to write that at fraction is 7 over 2. Okay? So there you go. So 7/2 is the coefficient. So 2 times 7 over 2 will be 7. So you'll have 7 on this side. You'll have 7 on this side. But you can't leave a coefficient as a fraction normally. And by the way, the coefficient in front of C2H6 is 1. So you can't leave this as a fraction. So the way you get rid of that fraction, that denominator, is you multiply everything through by 2. So this is going to be 2, I'll write it down here, 2C2H6 plus 2 times 7, 2 times 7 over 2 is going to be 7O2. 2 times 3 is 6. 2 times 2 is 4. Okay, and that's your final answer. Again, if you wanted to use the box method, you could do this, and you write C, C, H, 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 and you keep adding boxes to whichever side has the least, okay? Go back and review that video. It's either lesson 9, 10, or 11, somewhere in there, okay? All right, next. What type of bond does NaCl have? Well, that's a crystal lattice structure. NaCl is an ionic bond. It's a metal, Na, over on the left side of the periodic table, a weak guy, and a strong guy, a non-metal, a chlorine, way over on the right side of the periodic table. So the chlorine takes the electron away from the sodium. Chlorine becomes negative, sodium becomes positive, so they attract each other. That's an ionic bond. Okay. All right. Ionic bonds is back in the foundations unit. Okay, about lesson number 7 or 8, somewhere in there. Okay, which of the following is not possible? So this is where it's helpful to have your periodic table of charge numbers, the one with all the charges, but you don't need it. Okay, so let's look at this. O2. So if atoms, either nonmetals over here or these alkali earth metals, are going to ionize to be like the nearest noble gas. So for oxygen to be like the nearest noble gas, neon, it wants to pick up 2 electrons. So it has 8 electrons. So 1, 2. So that's a 2 minus. So that one's okay. I'll just put a little check mark. Krypton. Krypton with no charge on it. Well, that's what a noble gas has. Noble gas is not going to ionize. It's not going to gain or lose electrons. So krypton is fine. Okay, calcium. So calcium, to be like the nearest noble gas to calcium is back in the row before. You go backwards. 1, 2 to be like argon. So calcium's going to be a 2 plus. This one's a 1 plus, so that's the one that is not possible. Calcium cannot be a 1 plus. Lithium can, right there. It wants to lose 1 electron to go back and be like helium. So lithium does take on a 1 plus charge, so that one's okay. So the answer is calcium, okay? That's all you have to do, circle it, okay? I want you to get through this fairly quickly and easily, all right? But be sure you understand why the answer is, because these aren't the exact same questions you're going to see on the district test. Be sure you understand the reasoning. Okay, give the chemical formula for the ionic compound of magnesium and fluorine. So first of all, we start with magnesium, and we come here, and it's in the second column here, so it takes on a 2 plus charge. It wants to lose 2 electrons to be like neon, so that's a 2 plus. Then we look at fluorine. Fluorine needs to gain 1 electron to be like the nearest noble gas, which also happens to be neon, so that's going to be a 1 minus. So what we do is we do the crossing arrows. Well, they don't really cross, but they go like that. Okay, so that's going to be the subscripts there. So magnesium is going to have a subscript of 1. Fluorine is going to have a subscript of 2. You get rid of the negative signs, by the way. And of course, the subscript of 1, you don't write it. So it's just MgF2. Okay, and that's the answer. Okay, so that would be how you create that, all right? And again, that's back in about lesson 8. It's back in the ionic bond lesson. Okay? All right, let's keep going. (19) Identify which atom in the second row has the largest atomic radius and which has the smallest. Explain why. Okay. So this comes into Z number. You don't have to calculate the Z number. But everything in the second row has 2 orbitals, has a second orbital. That second orbital is the valence orbital. So no matter how many electrons it has in the valence orbital, neon has 8, lithium only has 1. They're all the same distance from the nucleus. So they don't shield each other. Remember, that means they block each other from the nucleus. They don't shield each other. So what happens though is as you go over in this direction, you add protons. You add electrons, but you add protons. But the electrons don't shield, they don't block each other. But you keep adding protons, which pull harder and harder on those electrons. So the smallest is going to be neon. Even though it has 10 protons and 10 electrons and about 10 neutrons, even though it has a lot more protons, neutrons, electrons than lithium, it has the protons pull in on the electrons. It pulls them in tighter. So this is going to be the smallest. Lithium's going to be the biggest because lithium only has 3 protons to pull in. It only has 1 valence electron, but it only has 3 protons to pull on it. So it's going to be the biggest. So this is the one that seems a little odd or a little strange about. You would think with the fewer protons and electrons and neutrons it would be smaller, but it's not. This is bigger, and over on the right this is smaller, okay? So the answer is neon has more protons to pull the valence electrons in, okay? So let's write that. Again, you can just write a real compact answer. Okay, that's it. Neon is largest because it has more protons to pull in the valence electrons. Okay, 20. We did this in class, okay? Would entropy of the following reaction be increasing or decreasing as it moves from reactants to products? So reactants on this side, products on this side. I didn't ask you to give the reasons why, but let's do that. So first of all, it's going from liquid to gas. That's greater entropy. Remember, entropy means disorder. Okay, so disorder. So going from liquid to gas, so liquid to gas, that's one reason. The other is you have 4 moles, even though it's a very complex molecule. You have 4 moles here, whereas over here you have 6 plus 1 plus 12 plus 10. You got a whole lot more moles on that side. So it's fewer moles to more moles. Again, moles simply means numbers of molecules. So you have a lot more molecules over here than you had over there, or particles in general. Okay? All right, 21. Let's keep going on this. All right, this is one that was in the very last, the acid-base lesson. And so it's a tough problem, but the one on the test looks exactly like this, except the numbers are different. Okay, so follow the reasoning in this. What a titration is, it's when you drip an unknown acid into a known amount of base. You know the volume and you know the molarity, how many moles per liter there are of that base. And we're going to just say it's NaOH, all right? So you do that so you can figure out the concentration of the unknown acid. Now, how do you do that? Why does it do that? Because when you drip an acid into a base, it neutralizes. It takes one acid molecule to neutralize with one base molecule, and that becomes neutral. Now you could say, well, so what? How do you know when it's neutral? How do you know when that's happened? And there's something called an indicator. And what it does is, it's kind of magic how it does this. It's actually a study in itself that we don't need to understand how it works. But as soon as you have exactly the same number of molecules of acid as base, that means you've neutralized them all. You basically turned them into what's called salt. Not exactly the kind of salt you put on your, it could be the kind of salt that you put on your food, but there's all kinds of other salts. And it turns it into water. So it's a neutral solution. So once the number of acid molecules equals the number of base molecules, these indicators kind of magically change the color of the solution. It goes from being perfectly clear, like almost looking like water, to all of a sudden, bam, it's bright pink. All of a sudden, literally just suddenly happens. Or bright blue. Depends on what kind of indicator you're using. So you don't need to understand how that works. You just need to understand that it does happen. So what we need to do is, we know that the neutralization is going to occur when the number of moles, basically the number of molecules of acid, equals the number of molecules of base. So the first thing we have to do is, we have 25 milliliters of 0.3 molar base. So we have to figure out how many moles that is, okay? So we need 1 mole of, the exact same number of moles of acid as base for it to be neutralized. Okay, so what you do is, first thing you got to do is you got to turn 25 milliliters into liters. Why? Because molarity, which is this, is moles per liter. So since this has got units of liter, you got to change this to units of liter. So 25 milliliter, and the conversion is there's 1 liter for every 1,000 milliliters. Okay, so milliliters cancels, and I should put a base solution here. But anyway, it's okay. And what that equals is 0.025 liters. Okay? So that's how many liters. What you learn to do after a while is, rather than doing this formal calculation, you just take the decimal in the 25 milliliters, move it 3 places to the left, put it right there, put a 0 there, and it's 0.025, okay? So you don't always have to do this formal calculation. Okay, so now we know how many liters. To know how many moles, we take 0.3 moles per liter and multiply by the number of liters. And that the liters will cancel out. That will give us moles. So let's go ahead and do that. Remember, anytime you're using molarity, you convert it from capital M. You can't work with that. You convert it into moles, and it's of the base per 1 liter of the solution. We're always talking about the entire solution, okay? Then you're going to multiply that by 0.25 liters of the solution. So liters of solution cancels there and there. You're going to end up with moles. So you get out your calculator, and what that's going to give you is 0.0075 moles of base. Okay, I'm writing kind of small there, but that's moles of base, whatever the base happens to be. So for this to neutralize, you have to have the same number of moles of acid. So I'll write that down here. I'm going to come over here, kind of jumping around here. So 0.0075 moles of base. So to be neutralized, it's got to equal 0.0075 moles of the acid. Okay, that's a 5 there. Okay, so what it's asking is, what is the concentration? What is the concentration of the acid? So what is concentration? It's molarity. It's moles per liter. So we know the number of moles right there, and it tells us that we have 30 milliliters. Okay, so rather than do this formal calculation, I'm just going to do my decimal thing. I'm going to slide that over. So that equals 0.03, whoops, writing it up too high. So the molarity, so the concentration of the acid, and you write that with the square brackets, concentration of acid, that's what we're looking for, equals the moles right here. And that's of acid, because we have to have that number equaling the moles of the base, over, and this number, 30 milliliters, is equal to 0.030 liters. Again, we took the decimal from behind the 0 right there and moved it over 1, 2, 3 positions, and that's liters. Okay, so that's going to equal, right here, I'll write the answer here, just do the calculation. 0.25. And that's the concentration of the acid. And that's molar. And that's your final answer. Okay, I'll put a little star because there's a lot of writing on this. Okay, let's review that. We neutralize when we have the same number of particles of molecules or moles of acid as base. That's when it neutralizes, and we know that because the indicator changes to bright pink. All right, so we figure out how many moles of the base. That's what we know. We know we have 25 milliliters, and we know the concentration of the base. So we figure out, we turn milliliters to liters right there. Okay, and it is 0.025. All right, now we take the molarity, which is moles per liter, so 0.3 moles of base per liter of solution times the amount of solution we have, 0.025, will tell us how many moles of base. Okay, for the base and the acid to neutralize, we have to have the same number. So over here, same number of moles of base as acid. So we know how much acid we have. So the concentration of the acid, which is what the question is asking for, it's not asking for number of moles, it's asking for molarity, for concentration, is going to be the moles, which is 0.0075, over the volume, the liters. And we turned 30 milliliters into 0.030 liters, okay? So the same way we did it over there. All right, and so that you divide that, you get 0.025 moles per liter is the concentration of the acid. So that's the final answer. Okay, I'm going to break this video right here and continue on another video.